In this video, I'm going to cover everything that you need to know for GCSE Vectors, from the basics to the hardest grade 9 questions. Okay, so we're going to start by looking at vectors in the column vector format. Okay, so a column vector in 2D, which is what you focus on in GCSE, is written like this. So you have sort of a long bracket, okay, and then you'd have a number at the top and then a number at the bottom, and then closed bracket here. So this is our column vector format. Now what we have to discuss is, what does this x and this y represent? Well, the number at the top, which I'm calling x for now, okay, is called the horizontal component, or it might be called the x component, because this tells us how much we have to move to the right or to the left. If it's positive, it's to the right. If it's negative, it's to the left, just like coordinates. Then our y component can be called our vertical component. Okay, and this tells us how much we move up or down. Okay, so up would be positive and then down for negative. Okay, so once again, just link directly to coordinates. Now, there is no line between the two numbers like a fraction, so do not draw a line there. Okay, that is incorrect. Okay, it's not a fraction, it is a vector. So let's look at a numerical example of a vector. So I could write the following here. So I'm going to write a number at the top, let's go with 3, and then a number at the bottom, -4. Okay, so 3 would be my horizontal component, -4 is my vertical component. So let's just discuss exactly what they're representing. Well, the 3, because it's positive, represents 3 right. And then the -4 represents, because it's the vertical component, because it's negative, it's going to represent 4 down. Okay, because the downwards direction is negative. Then let's look at another example. So let's go with -5 and then +2. Okay, so now our horizontal component is negative. Okay, so it's not going to be 5 to the right, it's going to be 5 to the left instead, because the negative direction is the left direction. And our vertical component is positive, so that is going to be 2 up, like that. Now, in terms of naming our vectors, we use lowercase letters. So I could call this first one A, and I could call this next one B. However, we would either write these letters in bold, which is hard to do handwritten, or we would underline them to indicate that they are vectors. Okay, so you'll see me regularly underlining our letters during this video. Now we're going to look at drawing vectors. Okay, so we're given 2 column vectors here. The first one is -2, 3. Now we're given no information about where this should start, so therefore you can start wherever you want. Okay, so just pick a point on your grid. So I am just going to go with this point here. Okay, that's my start point. Now let's think about what our components are representing. Okay, so the -2, because it's negative, this is representing 2 left. Okay, so I'm going to start by going 2 to the left. So 1 and then 2, like that. I'll just write a 2 there just for reference. And then the 3 here represents 3 up because it's positive, and that is your vertical component. So I'm now, from where I've ended up, going to go 3 upwards. So that'll be 1, then 2, then 3, like that. And I'm just going to write a 3 there. Now that drawing I've done so far is not your answer. Okay, we just figured out our start point and then our end point. Our drawing is going to connect them up. Okay, so what I'm going to do is draw a straight line joining those 2 points together. And importantly, you are going to put an arrowhead on that line to indicate which direction you're going. Our start point was down here in the bottom right. Our end point was up here in the top left. So therefore, our direction of travel would be like that. So I just put my arrowhead on there because vectors have direction and we need to indicate that, okay, on the diagram, which I have done there. Now let's do the 4, -5. Okay, so let's pick another point to start with. I'm going to go over here. Okay, and the 4 represents 4 to the right. Okay, because it's positive and it's our horizontal component. So I'm now going to travel 4 to the right. So 1, 2, 3, 4, like that. I'm just going to write a 4 here. And then the -5 represents 5 down. Okay, so from where I ended up, I'm now going to go 5 down. So 1, 2, 3, 4, 5. And I end up here. So we got our start point and our end point. So we can now join them up with a straight line, which I'm going to do in red. And our direction of travel would be like this. Okay, so the arrowhead would be going like that to indicate our direction. Now we've talked about drawing vectors and direction. The next key word we need to talk about is magnitude, because vectors have magnitude as well. Now, magnitude is another word for length. So you can see those red lines I've ended up drawing, they have length, okay, they have magnitude, and you will be expected to potentially calculate its magnitude. Okay, so in order to do this, we're going to recognize that I have drawn over here, if we look on the left, a right angled triangle. Okay, now what could we use to calculate a length in a right angled triangle? Well, you could use Pythagoras' theorem. Okay, so Pythagoras' theorem is a squared plus b squared is equal to c squared, where c is our hypotenuse, our longest length, the one that is opposite the right angle. And what you'll find is that our vector, our red line, is always going to be the hypotenuse. So this is the easiest case for Pythagoras. If I want to calculate this length here, we are going to do the square root of 3 squared plus 2 squared, okay, and then you would just have to calculate what that comes out as. Okay, so 3 squared is 9, 2 squared is 4, so we're going to get the square root of 13. Okay, and just check, can I simplify that? Okay, no, I can't, so that can be our final answer for that vector there. Now, in terms of some notation we could use, if I write the vector we were dealing with there, okay, the vector we were doing was the negative 2, 3. I'm just going to write it down here. What you could do is put magnitude symbols around it, which is just vertical lines. And I would say that this is equal to the square root of 13, like that. Okay, let's do our other one then. Okay, what we could do is we're going to write our right angle here. And once again, we're finding the hypotenuse. It's always the hypotenuse. So the calculation we would do is the square root of 4 squared plus 5 squared. Okay, now 4 squared is 16, 5 squared is 25. We add them together, we get the square root of 41. Okay, like that. So now I can clearly write out my magnitude. So the vector we were dealing with was this one here. So I'd write that the magnitude of, and it will be 4, negative 5, is equal to the square root of 41. Okay. Now we can generalize this, because what you'll find is we're essentially doing the same thing every single time. Okay, let's say we had a vector which was xy, and I wanted to calculate its magnitude. Well, what you'd end up doing is you'd square root, and you'd square each component. So we'd do x squared, and then we'd add it to y squared. Okay, and that would be our generalization. You do not need to draw a vector out to calculate its magnitude. You could just use that formula. So for example, what I could do is if I was to write out a different vector down here, I might write 5, negative 2. And let's say I need to calculate its magnitude. I'd put the magnitude symbols on, and then I'd write equals to, and it will be the square root of 5 squared plus, because the negative 2 is negative, we're going to put it in brackets for correct notation, and then we're going to square it. Okay, and then 5 squared is 25, negative 2 squared is positive 4, so we end up with 29 under our square root. Now, some other notation we can use in terms of labeling vectors. I'm just going to talk through that now. So I'm going to do this in a different color. And what I could do is I could go to one of the points that my vectors start at. So if I go to this point here, and I could label it capital A. So we do that for points, would use capital letters. And then for my end point, I might label it capital B. So I could name this vector in a different way. What I could write, which I'll write at the top here, I could write A, because that's where we started with, then B, and then do an arrow like this to indicate we are going from A to B. Again, A to B would be equal to my vector negative 2, 3, like that. So let's do it on the other vector. Okay, so I'm going to call my start point, we'll call it C, and I'll call my end point capital D. Okay, so what I can say is that C to D, with a line going in this direction, is equal to, and it was the vector 4, negative 5, like that. What we're going to discuss now is return vectors. Okay, so we've got the vector going from A to B, and we got the vector going from C to D. But let's say I wanted to know the vector going from B to A, so I wanted to swap the letters around. And let's say I wanted to know the vector from D to C. Okay, so let's go and investigate beta A. So if I go to my vector here, what I need to do, if I want to go in the opposite direction, I'm going to take this arrow off, okay, and I'm going to draw it going the other way, okay, like that. Okay, and I want to know the vector represented by that line with that arrow there. So what I'm going to do is I'm going to draw a right angle triangle around it, like this, okay, going like that, and then like that. Again, I need to figure out then how much have we moved right or left, and how much have we moved up or down. So what you can see is I've moved 2 to the right. So therefore my horizontal component is going to be positive 2. And I've moved 1, 2, 3 down. So therefore my vertical component is going to be negative 3 like that. So I've got my return vector. Now let's do it for the C to D. So I'm going to go to my vector and I'm just going to reverse the arrow. So it's going from D to C instead. And then I'm going to start at D and create a right angle triangle. So I have to go to the left, okay, like that. And then have to go up in order to get to C like that. Okay, so I went 4 to the left. And then I have gone 5 upwards. Okay, so in terms of as a vector, if I'm going 4 to the left, that's negative 4 as my horizontal component. If I'm going 5 up, that's positive 5 as my vertical component. So I've got my return vectors there. But I want to think about what is the relationship between the pairs of vectors that I have got written there. Okay, so we have this pair here and then this pair of return vectors as well. Okay, what is the relationship? Well, if we look between negative 2 and 2, well, you'd multiply by negative 1. And if we look between the 3 and the negative 3, well, you'd multiply by negative 1. Let's just check that makes sense on the other pair of vectors. 4 to negative 4, you'd have to multiply by negative 1. Negative 5 to positive 5, you'd have to multiply by negative 1. So if you multiply both of your components by negative 1, so in other words, if you multiply your vector by negative 1, you will get the return vector. So beta A in general is going to be equal to the negative of A to B, like that. Okay, so you shouldn't have to draw out a diagram to figure that out. So for example, if I gave you E to F was equal to, and let's say it was negative 5 and then 7, then if I asked you to find what is F to E, so going in the opposite direction, the return vector, I'd multiply the negative 5 by negative 1 to get positive 5, and then multiply the positive 7 by negative 1 to get negative 7, and that would be my final answer. What we're going to look at now is resultant vectors. And in order to demonstrate this, I'm going to do this little task here where I'm going to draw the vector 3, negative 4. And then we're going to follow that with the vector negative 2, 6. Okay, so they're going to be connected to each other. Okay, now in terms of where I start, there's no point specified, so I can start wherever I want. So I'm just going to pick this point here as my start point. Now the 3 is our horizontal component, so that means 3 to the right. So we're going to go 3 to the right like this. Okay, and then the negative 4 is our vertical component, that represents 4 down. So we're then going to head 4 down like that to there. And that would be my endpoint. Now I'm going to join them up, okay, and draw on my vector with its arrow. So we'll be going like this, and the arrow would be in this direction here. Okay, what I'm actually going to do is I'm going to just rub off this working here just to declutter things a little bit. Okay, let's do my other vector then. So negative 2, 6. So from this point here, which is where I've ended up, we're going to do negative 2 as our horizontal component. So that means 2 to the left. So we're going to go 2 left, like that. Okay, and then our vertical component is positive 6. So that means 6 up. So I've now got to go 6 up. So 1, 2, 3, 4, 5, 6, like that. Okay, and I'm just going to put my endpoint there. And I'm now going to draw on my vector for that second movement I've done. So it's going to be from this point down here up to this point here. Okay, and I'm going to put my arrow on like that. And once again, I'm just going to rub out those lines that I did to help draw my vector. So the resultant vector would be how did I get from my initial start point to my very final end point here. Okay, so I'm now going to draw on my resultant vector, joining up those 2 points. So we'll be going like that, and then my arrow would be like that. And what I want to write out is what vector represents that movement. So I'm going to write resultant here. And then let's figure out what vector that would be. So if we're starting here, we're going 1 to the right. Okay, so my horizontal component will be positive 1. And then we've headed 2 upwards. Okay, so my vertical component would be positive 2 like that. And this would be the resultant vector of these two vectors up here. Essentially, it's the quickest route from our very start point to our very end point. Essentially, what is the result of what we've ended up doing? Now, I do just want to think, what was a faster way of getting that answer without drawing all of that out? Okay, so what I want you to think is, how is this vector and this vector here linked to my very final resultant vector down here? What is the relationship between all of them? If we look at our horizontal components, we got 3 and -2, and then we've ended up with 1. Well, if we did 3 plus -2, that does give me 1. Okay, let's see if this checks out for our vertical components. So in our vertical components, we've got -4 and we've got 6. Okay, if we add those together, I believe we get +2, and that checks out with what we've got here. So in order to find a resultant vector, you need to add up all of your vectors that you're doing. So as a generalization, the resultant of vector A, which I'm going to write and underline it to indicate it's a vector, and vector B, I'm going to underline that as well, would be A plus B, like that. So let's have a look at another question where we're going to make use of this idea of adding the vectors to find the resultant. Okay, so we've got find the resultant of these 3 vectors here. So if I want to do this in the quickest way, we don't want to draw things out. What I want to do is take all 3 vectors and we need to add them together. So we'd have 5, -1, -2, -4, and 7, 8. And we just want to add all of these vectors together. And to add them, essentially what we do is you add all the horizontal components together. So we got 5 plus -2, so that's going to give me +3, plus 7, that's going to give me +10, like that. Then we're going to add up all of our vertical components. So -1 plus -4, so that's subtraction, so that's going to be -5, plus 8, that's going to get me to +3. Okay, and this will be my resultant vector of those 3 there. Now we're going to have a look at vector operations. So vectors can be added and subtracted by adding the horizontal components together and adding the vertical components together, or subtracting if we're dealing with subtraction. Now we've already seen this a bit with our resultant vectors. So you can see this first question here as an example of addition, which I've already covered a little bit of. Okay, so to add these 2 vectors together, what we're going to do is go to the horizontal components and add them together. So 2 plus -6, well, that's going to be subtraction. So 2 subtract 6 is -4. And then for our vertical components, we got -3 plus 1. Okay, that's going to become -2 like that. And that would be my final answer. Now let's do some subtraction. Okay, so we're just going to subtract our horizontal components and subtract our vertical components, and we should get our answer. So for our horizontal ones, we're doing 2 subtract -6. So if you're doing 2 subtract -6, well, that's the same as addition. So 2 plus 6, so that's going to be 8. Just be careful with those negative signs, okay? Because a common incorrect answer to that component would be -4 if you just did 2 subtract 6. But you've got to account for the fact there's a negative sign here as well. Now let's do our vertical components. So -3 subtract 1. So that's going to give me -4, like that. Okay, and that's what we get from subtracting our vectors. Now let's consider some multiplication. So vectors can be multiplied by a scalar. So what is a scalar? Well, a scalar has magnitude, so it has length, but it has no direction. So an example of a scalar would just be a numerical value on its own. So for example, 6 is a scalar. So it's got magnitude, it's got length, okay, it's the size of 6. Okay, however, it doesn't have a specific direction, so therefore it's a scalar. Another example could be a negative number like -4. Okay, so numerical values are the types of scalars that you're going to be dealing with. So if we consider a vector, which is not a scalar, the individual components of our vector are scalars, but the vector as a whole, because it has direction, is not a scalar. Now, vectors can be multiplied by a scalar, and how we do this is we multiply the horizontal component and the vertical component by that scalar. So if we look at what we've got here, we've got -5, the scalar, multiplying our vector. So we're going to do -5 multiplied by 2, which is -10, and then -5 multiplied by -3, which would give me +15. Okay, and that would be my answer. Two vectors cannot be multiplied together in the same way they are added or subtracted. Okay, you shouldn't have to multiply vectors at GCSE level, so don't worry about that. If you look at vectors at higher level, you might learn about some other operations we could potentially do that involve multiplying components. So let's have a look at some other questions. So here we've got A, which is in bold, so that means it's a vector. Of course, I would underline it if I was to write it out, because I can't write in bold. And that's defined as -2, 3. And then we've got a different vector B, which is defined as 4, -5. Now we need to find 2A subtract 3B. And note the 2 and the 3 are not in bold because they are scalars, okay? They're not vectors. So I'm going to write 2A subtract 3B here. I'm going to underline my vectors. And what I'm going to do is replace both of my vectors with their column vector representation. So I would write 2, and then the vector for A, which is the -2, 3. And then we're going to write the subtract symbol. And then we're going to write 3 multiplied by our vector, column vector representation of B, which is 4, -5, like that. Okay, because now I've got a better calculation to work with. So now the next thing I'm going to do is get those scalars multiplying the vectors into the vectors by multiplying. So this 2 is going to multiply both of the components in our first vector. So 2 times -2 would be -4. And then 2 times 3 would give me 6, like that. Okay. Now just be careful with this second part, as there's sort of two ways of approaching it. What we could do is we could multiply the vector by 3. Okay, now if we do that, the subtract symbol here has to remain. So I'm going to put that there. And let's multiply both components by 3. So 3 times 4 give me +12. And then 3 times -5 would give me -15, like that. There should still be a subtract in the middle because we haven't actually used that. Now we can subtract our two vectors like before. So we're going to do -4 subtract 12. So that's going to give me -16. And then we're going to do 6 subtract -15. So that's going to be addition, okay, because if you're doing 6 subtract -15, subtracting a negative is addition. So 6 plus 15, which gives me 21. And that would be my final answer to 2A subtract 3B. Let's have a look at another question involving a little bit more algebra. So we need to find the value of x and y in this equation here. Okay, it's an equation because we've got our equal sign. So we need to make use of both sides. Now, in this scenario, when you're trying to solve an equation involving vectors, the first thing I'm going to do is try and write both sides as a single vector. So you see the right-hand side, it's written as a single vector. That's fine. I'm not going to touch that. But the left-hand side is written as this addition. So I want to write this as one single vector. So what I'm going to do to get this process started is I'm going to multiply both of the vectors by the scalars multiplying them. Okay, so in the first instance, we got 2 multiplied by 4, which is 8, and 2 multiplied by the y, which is 2y. And then we have this plus here, and then 3 is multiplying our vector. So 3 times x is 3x, and 3 times -1 is -3, like that. And then close our vector is equal to, and I'm going to leave the 23, 1 as it is. Now the left-hand side is still not written as a single vector. We've got an addition of two vectors. So let's actually add them together. So let's add our horizontal components. So 8 plus 3x. Well, I can only write that as 8 plus 3x because they're not like terms. Looks complicated, but you'll see why this is useful. Then 2y plus -3. So adding a negative is the same as subtraction. So we get 2y subtract 3. And then let's close our vector. And that's equal to 23, 1. So now we have a single vector on the left-hand side and a single vector on the right-hand side. The only way these vectors are going to be equal to each other is if their horizontal components are equal, and then separately their vertical components are equal. So now we're going to equate them. Okay, so let's start with my horizontal components. We're going to write 8 plus 3x is equal to 23. Okay, that statement must be true if the vectors are going to be equal. And then separately, I can take my vertical components and I can equate them. So 2y subtract 3 must be equal to 1. Now I have some simple linear equations that I can solve to figure out x and y. So for this first one, we're going to subtract 8 from both sides. So we get 3x is equal to 15. And then we're going to divide by 3. So we get x is equal to 5. So it comes out as an integer, but it doesn't have to be an integer. It could be a fraction. Now for our second equation, we're going to add 3 to both sides. So we would get 2y is equal to 4. And then divide by 2 on both sides. So we get y is equal to 2, like that. And those would be my final answers. Now, it is possible you could end up in a scenario with simultaneous equations where you've got x and y in both equations, and you might have to deal with that as well, which is a more complicated type of question. But the general approach to what I've done to get the equations should always be the same. So we're now going to look at parallel vectors and the relationship between them. So we need to determine if these 3 vectors here are parallel to 1, 2. So we're going to demonstrate this by drawing the vectors out. So I'm going to start with the vector 1, 2. So I'm going to pick a point. Okay, we'll go with this point over here. And we're going to do the vector 1, 2. So that means 1 to the right and 2 up, like that. Okay, so my vector, if I was to draw on my line, would be like this. Okay, so that's the vector 1, 2. I might just annotate that next to it. 1, 2. Now let's work our way through some of the other vectors we've got here. So let's go with -2, -4. Okay, so let's pick a point. We'll go here. And then -2 for the horizontal component means 2 to the left. Okay, and then the -4 means for the vertical component 4 down. So we end up down here. So let's draw in my vector line. So it's going to go like this in that direction. Okay, and that is the vector -2, -4. Let's move on to our next one, which is 3, 6. Okay, so I'm going to pick a point. We'll go with this point here. And then we're going to go 3 to the right for our horizontal component, and then 6 up for our vertical component. So we end up here. So let's draw in my vector line. Okay, and it looks like that. Now our final vector we got to do is 1, 4. Okay, so I'm going to pick this point over here. Okay, and our horizontal component for this vector is 1 to the right, and then we've got 4 up. So it'd be like that. Okay, and let's draw in our vector line, which would go like this. And I'll put my arrow on. Okay, and let's just annotate that is the vector 1, 4. And the vector before that was 3, 6. So let's look at the 4 lines I've drawn. And we're going to compare the other 3 to this one here and decide if they're parallel. So just a reminder on the definition of parallel. Okay, so you've got sort of a few definitions that are often given to you, such as the lines will never meet, okay, or they've got the same gradient. Okay, so if we look at the 4 lines I've drawn, well, of the other 3, which of them have the same gradient as this one here? Well, it would be this line here and this line here. You'll see that the other one has a different gradient, so is not parallel. So what I've determined is that the vectors, and it would be 3, 6 and -2, -4 are parallel to 1, 2. So 3, 6 and -2, -4 are both parallel to 1, 2, which I'm just going to write here. Now, what I want to think about next is what is the relationship between 1, 2 and its parallel vectors? Well, if we look at our horizontal components for this first one here, in order to get from 1 to 3, you'd have to multiply by 3. In order to get from 2 to 6, you'd have to multiply by 3. Let's check for the other one. To get from 1 to -2, you'd have to multiply by -2. To get from 2 to -4, you'd have to multiply by -2. Okay, so the relationship between these vectors are that they are scalar multiples of each other. If we take the vector 3, 6, what I could do is I could factorize 3 out of this, which is what I was multiplying by, and I would get 3 lots of 1, 2. So clearly 3, 6 is a scalar multiple of the vector 1, 2. Now we could do similar for the -2, -4. Okay, this time I could factor -2 out. So I'd get -2 and then I'd get 1, 2. So clearly the -2, -4 is a scalar multiple of 1, 2. Now let's check it for the non-parallel vector. So the vector 1, 4. Okay, if I write that over here, we'd have 1, 4 and then 1, 2. Well, in order to get from 1 to 1, you'd have to multiply by 1. To get from 2 to 4, you'd have to multiply by 2. So clearly the vectors are not scalar multiples of each other, so they are not parallel. So in general, the key fact is that vectors are parallel if they are scalar multiples of each other. So what this means is if I gave you a vector, so for example, if I gave you a random vector, we'll go with 5, -7. If I ask you to state a vector which is parallel to this one, all you would do is multiply both components by the same number. So let's just go with 4. If I multiply by 4, I would get 20. And then if I multiply by 4, I would get -28. Okay, so these two vectors are parallel to each other. Now we can link this directly to gradient, because if we had the vector 1, 2, which is what we're dealing with here, well, our x component represents our change in x, and our y component represents our change in y. So if you want to calculate the gradient, often we use the letter m, it's the change in the y, which is the 2, divided by the change in the x, which is the 1. So the gradient would come out as 2. Now let's do this for one of the parallel vectors. So one of our parallel vectors was -2, -4. Well, the -2 is the change in x, as it represents how much we move in the horizontal direction. The -4 would be the change in y. So if I wanted to calculate gradient for this one here, I would do m is equal to our change in y, which is -4, divided by our change in x, which is -2. Okay, and that comes out as +2 as well. Okay, and that will happen providing that this number here and this number here are multiples of these two numbers, because that makes them equivalent fractions. So we've got a couple of questions involving parallel vectors to consider here. So it says write a vector parallel to the x-axis. So the x-axis is our horizontal axis here. Now let's draw a line which is parallel to the x-axis. So I'm going to go with this here. Okay, and because it's going to be a vector, I'm going to put an arrow on it. So let's write out the vector for this line here that I've drawn with this arrow. Okay, so we've gone 4 to the right. So our horizontal component is going to be 4. And then we haven't moved up or down. So our vertical component is going to be 0, like that. Now let's find another vector which is parallel to the x-axis. So I'm going to go down here and draw a different one. Like that. Okay, I'll put my arrow on it. Now once again, let's write out our column vector. So from our start point to our end point, we have gone 6 to the left. So that will be -6. And we haven't gone up or down. So our vertical component is going to be 0. So in general, for a vector parallel to the x-axis, your horizontal component will be some non-zero number, and then your vertical component will definitely be equal to 0, like that. And that vector will always be parallel to the x-axis. Now let's do parallel to the y-axis, and you might be able to guess what's about to happen. So our y-axis is our vertical axis, so let's draw something that's parallel to that. So we'll go with this here, and I'm going to put an arrow on it. Okay, so let's write out our column vector. So we haven't moved to the left or to the right from our start point, so it's going to be 0 for a horizontal component. And we've gone 4 upwards, so I'm going to put a 4 as my vertical component like that. Okay, and that will be a vector parallel to the y-axis. Now if I was to do one more, let's go down here. Okay, like that. I'm going to put my arrow on it. Okay, so once again, we haven't moved to the left or to the right, so our horizontal component is 0. And it seems that we moved 5 down, so our vertical component is -5. So in general, if you want a vector parallel to the y-axis, it would have to be 0 for our horizontal component, and then our vertical component will be some non-zero number k. Of course, it doesn't have to be integers, it could be fractions, that's fine. Now let's look at a different type of question involving parallel vectors. So it says show that the vector 6, -5 and 30, -25 are parallel to each other. Okay, so there are a few ways you could do this. What I'm going to do is I'm going to take the 30, -25, okay, and I'm going to factor out a scalar factor such that I end up with 6, -5 in my vector. Okay, so what would I have to multiply 6 by to get to 30? Well, it would have to be 5. What would I have to multiply -5 by to get to -25? Well, it would have to be 5. So this statement makes sense. You can then say, therefore, 6, -5 and 30, -25 are scalar multiples of each other, so they are parallel. Like that. So that's what you'd be expected to do in a show that question. Now I do just want to think of another way of approaching this. So if I write the vectors out here, if they're parallel, essentially there is that common number that we could multiply both the horizontal and the vertical component by, okay, in order to get to the other vector. Now in this scenario, it's pretty obvious it's 5, but let's say you were unsure. Okay, let's say you were unsure what number you had to multiply by, so let's just call it k. Okay, so in our first instance for our horizontal component, I'd be doing 6 multiplied by k is equal to 30. So if I wanted to find out what k was, I'd have to do k is equal to 30 divided by 6, which gives me 5, which is the expected answer. Now let's apply some similar logic to our vertical components. Okay, so we've got -5, and we're going to multiply by k, and that should be equal to -25. Well, I'd have to divide by -5, so k would be equal to -25 over -5, which also comes out as 5. So if you have parallel vectors and you divide your horizontal components and then divide your vertical components in the same direction, then the answers for both calculations should be equal to each other. And we're going to make use of that in a second. So let's look at a harder algebra question then. So we got the vector c, which is equal to 2x -5, and the vector d, which is equal to 3x. And we're given that c plus d is parallel to 3, 4. And we need to find the value of x. So the first thing I'm going to do is figure out what is this vector c plus d. Okay, so c plus d, and I'm going to underline my vectors, would be equal to, so c, which is 2x -5, plus d, which is 3x, like that. Now I want to write this as a single column vector, so let's add them together. If we add our horizontal components, we get 2x plus 3. Add our vertical components, we get -5 plus x, like that. And the idea is this vector here, 2x plus 3 and then -5 plus x, is parallel to our other vector given in the question, so the 3, 4. Okay, so we can't set them equal to each other, okay, because they're not necessarily equal to each other. We're just told that they're parallel to each other. Well, we know if they're parallel, then in order to get from 2x plus 3 to the 3, I have to multiply by some value. And then to get to from the -5 plus x to the 4, I'd have to multiply by the same value. Now, in order to figure out what this value is, the calculation we can do for the horizontal components is 3 divided by 2x plus 3. Okay, so 3 divided by 2x plus 3, well, that would give me this value k. But also, if we consider my vertical components, in order to figure out k, I could do 4 divided by negative 5 plus x. Okay, so I can also say that k is equal to 4 divided by negative 5 plus x, like that. So I have two expressions for k, this one here and this one here. Well, if they're both equal to k, then both these fractions must be equal to each other. So I can say that 3 over 2x plus 3, which is this fraction here, must be equal to this fraction here, which is 4 over negative 5 plus x. So now I have an equation I can solve for x, so we can cross multiply. So we're going to multiply the 4 by this denominator, we're going to multiply the 3 by this denominator here. Okay, so on the left hand side, if I keep the 3 there, we got 3 lots of negative 5 plus x is equal to 4 lots of 2x plus 3, like that. Now we've got an equation to solve without fractions, so let's expand the brackets. On the left-hand side, 3 times negative 5 is negative 15, 3 times x is 3x. Then on the right-hand side, we're going to get 8x from 4 times 2x, and then plus 12 from 4 times 3. Then let's get our x's together, so let's put them on the right. So we're going to subtract 3x from both sides. So we get negative 15 is equal to 5x plus 12. And then I'm going to subtract 12 from both sides. So I get negative 27 is equal to 5x. And then finally, we can divide by 5 on both sides. And that is going to give me my final value for x, which should be negative 27 over 5, like that. Okay, and that's my final answer. We're now going to look at perpendicular vectors. So it says write down a vector which is perpendicular to 4, negative 3 and has the same magnitude. So remember that magnitude means length. So let's start by drawing this vector for negative 3. So I'm going to pick a point as usual. So we'll go with this point here. And then we're going to go 4 to the right for a horizontal component and then 3 down. Okay, so I'm going to end up down here. And let's draw in my line. So it'll be going like this. Okay, so that is the vector for negative 3. So what I'm going to do now is I'm going to draw a vector which is perpendicular to this. And I'm going to try and make it so it has the same magnitude. Okay, so if I was trying to draw a vector which is perpendicular, it has to be at a right angle. Okay, so what I would be doing would be drawing a vector going a bit like this. Okay, so that vector there, and I'll say it's going in this direction, that is perpendicular to my initial vector. So let's write out what is this green vector I've got here. Okay, well, we're starting over here. So we're going 3 to the right, and then we're going 4 upwards. So this would be positive 4, like that. Okay, that would be a vector which is perpendicular to that red one. But actually what we'll find is there is another scenario I could have drawn out here. So we'll do it in a different color. So if I'm to go to the bottom end here, I'm just going to mark it in purple. Now if I was to draw a vector going in a different direction, I could draw it going like this. Okay, and once again, that is perpendicular. Okay, that is at a right angle. This is a right angle here. And let's write out what my vector is. Well, if we're at this point, we're going 3 to the left. Okay, so it's negative 3 as my component. And then we're going 4 down, so it's going to be negative 4, like that. Okay, and what I want to do is just compare the 3 vectors I've ended up with. So the vector for negative 3, which was my starting vector here, is perpendicular to 3, 4. It is also perpendicular to the vector negative 3, negative 4. So how could I have obtained these answers without drawing all that out? Well, hopefully what you notice is that if you ignore the signs for a second on negative symbols, the 3 and the 4 have swapped around. Okay, so the 3 has shifted up here and the 4 has shifted down to the vertical component. And similar has happened here and here. Okay, so that's one change that's been made. Okay, so let's say I had a vector AB. I wanted to know a vector perpendicular to this. Well, I'd have to shift the A and the B around. However, there is one other change that has been made here, okay, which is important to note if you're going to get your perpendicular vector. The sign of the 3 here was negative, and then up here it is positive. Whereas the sign of the 4s have stayed the same. Okay, then for the other one, you can see that the signs of the negative 3s have stayed the same, but then we've got a positive 4 here, but a negative 4 there. So essentially, we've swapped the components around, and then we've changed the sign of one of them. In other words, we multiplied one of them by -1. So our perpendicular vector to AB could be potentially negative BA, or alternatively, it could be, if I write the B and A again, I could multiply the A by -1, so it could be B negative A. They're your two options. Now, why does this work? Well, it all links to gradient. Okay, so this here is our change in X. And then our vertical component is our change in Y. Now, if I was to write out my gradient M, it would be my change in Y, which is the -3, divided by my change in X, which is 4. Okay, and I could write that as -3/4. Now, if I wanted a perpendicular gradient, which I'm going to call MP, well, then you have to do the negative reciprocal of that gradient. Okay, so it's going to become 4/3, and then we're going to multiply by -1. Okay, and then that gives me my new perpendicular gradient. Okay, which then relates to my other vector here, because we've got the change in Y, which is 4 up here, and then the change in X, which is the 3, which goes down here. Okay, so it all links to gradient. But essentially, to find a perpendicular vector, you swap your components, and then you multiply one of them by -1, which is essentially the process for finding a perpendicular gradient. Then that process gets you two vectors which are perpendicular, but also have the same magnitude as the original vector. Now, what you could then do is go to your perpendicular vectors and multiply the horizontal and vertical components by the same scalar, and then that's going to get you another perpendicular vector which will have a different magnitude. We're now going to look at position vectors. Position vectors tell us how we get from the origin to a specific point, where the origin is the point 0, 0 on our axes. So let's look at this example here. The point B has the coordinates -3, 4. What is the position vector of B? So what I'm going to start by doing is marking the origin, because my position vector is always taken from the origin. So that's the point there. And let's mark the point -3, 4. So -3 is to the left, and then we got 4 up. So that would be this point here. So I'm going to label the origin O. That's often what we use to represent the origin. And then I've got the point B. Now, if I want to know the vector between those 2 points, what I'm going to do is I'm going to draw a line joining them up. And then the arrow would be going in this direction because I want to end up at B. So let's write out the position vector of B. Okay, we have gone 3 to the left, and then we've gone 4 up. So the position vector would be, if it's 3 to the left, it's going to be -3 for our horizontal component, and then it's 4 up, so it's going to be +4 for my vertical component. So hopefully you will see how it's directly linked to coordinates because we're always going from the origin. If you have the coordinates -3, 4, okay, our x coordinate is our horizontal component, and then our y coordinate is our vertical component. And the notation that we use for a position vector, because it always starts at O, it's going to be O to B with an arrow going like that, and it's going to be equal to. So let's say we had a point A, which had the coordinates x, y. Then if I wanted the position vector of A, that would be from the origin to A, like this, and that would be equal to the x-coordinate as the horizontal component, and then the y-coordinate as my vertical component there. So if you have the coordinates of a point, it is very easy to write the position vector of that point. So let's look at an application of this. The point C has the coordinates 5, -3. We need to figure out the position vector of C, and then subsequently, what is the distance of C from the origin. So let's start with my position vector. That would be O to C, because it always starts at the origin and I need to end up at C, and it's going to be equal to, my horizontal component is going to be my x-coordinate, which is 5, and then my vertical component is going to be my y-coordinate, which is -3. You do not need to draw a diagram to figure that out. Now we need to know what is the distance of point C from the origin. Well, I know how to get from O to C. Okay, that is my vector here, 5, -3. So that tells us how I want to move from the origin to C. So subsequently, if I was to calculate the magnitude of this vector, which we discussed earlier in the video, then that is going to give me the distance of C from the origin. Okay, so I want to calculate the magnitude of 5, -3. So our formula for that was to square root, and we're going to do our horizontal component squared. So it's 5 squared plus our vertical component -3 squared, like that. And if we were to calculate that, we would get the square root of 34, because we've got 25 and then we've got +9. If we add them together, we'd get 34 under our square root. So that would be the distance of C from the origin. We're now going to have a look at displacement vectors. Now, a displacement vector represents how we get from one point to another. So a position vector, which we just talked about, is a type of displacement vector, because a position vector tells us how we get from the origin to another point. Okay, however, displacement vectors in general don't have to start at the origin. They can start at any other point. So what I'm going to do is come up with a formula for a displacement vector in terms of position vectors. So let's say we have our origin, the point O, which I'll mark here, and then let's say there was some point A. Okay, and let's say I knew how to get from O to A. So in other words, I knew the position vector of A, which would be denoted O to A like this. Now let's say there was another point over here, and we're going to call it B. And let's say I knew how to get from O to B. Okay, so I'm going to draw that vector on. And of course, that would be the position vector of B, so O to B, like this. Then let's say I asked you to find the displacement vector from A to B. So essentially, how do I get from A to B? So that would be this vector here that I'm drawing on in orange, like that. Now, I need to find A to B using the other vectors written on my page. So we're starting at A and we're ending up at B. So I'd write that as A to B with the arrow going like this. Okay, so if I'm beginning at A, I'm over here. And what we need to try and do is make use of those black vectors that I've drawn. So what we could start by doing is going from A down to O. Okay, so I would write A to O. However, if we look at my diagram, the current vector I know is O to A, because that's going from O to A, but I want to get from A to O. Now that is the return vector. What is the relationship between a vector and its return vector? Well, they're multiples of -1 of each other. So instead of writing A to O here, this is equal to -O to A. So I'm actually going to replace this with -O to A, like that. And that will tell me how I get from A at the top here down to O at the bottom here. So we're now at O, so I'm just going to circle that in purple. And my end result, I want to get to B. Okay, so I want to get up here. Well, I know how to get from O to B. That's the vector OB. So what I'm going to do is I'm going to add that vector on to what I've got so far. Because if I want to do -O to A and O to B, essentially I want to do the resultant of the two vectors, and how we find resultant vectors is by adding our vectors together. So we managed to get ourselves a formula for the displacement vector A to B in terms of position vectors. I am just going to rewrite it slightly. I'm going to write the O to B at the start, and it's positive. And then I'm going to write the subtract O to A like that. So if you want to find the displacement vector A to B, what you have to do is do the position vector of B, which is your end point, your destination, and you need to subtract the position vector of A, which is your start point. So if you do your destination position vector, subtract your start point position vector, you'll get the displacement from those 2 points. So now let's make use of that formula. So we got a question here. The point C has the coordinates -2, 4, and the point D has the coordinates 7, -3. We need to find the vector C to D, so the displacement vector from C to D. So let's go through this information and just write out what we know. If the point C has the coordinates -2, 4, then I know the position vector for C, which would be O to C, and that is going to be equal to, and our x component, our horizontal component, is going to be our x coordinate -2, and then our vertical component is going to be our y coordinate +4, like that. Now, if we look at the point D, we also have its coordinates. So I can write out the position vector of D. That would be O to D, and that's going to be equal to 7, and then -3, like that. So I've got the position vector of the 2 points we're interested in. We now need to find the vector C to D. So if we look at the formula, which I have got over here, you do the position vector of your destination, which is D, so O to D, subtract the position vector of your start point, which is O to C, like that. So now let's substitute my column vectors in. O to D is this vector up here, so it's 7, -3. And then we're going to subtract O to C, which is this position vector up here, so -2, 4, like that. Now we just need to subtract them. So we've got 7 subtract -2, so that's going to be addition, so that's going to give me 9. And then we have -3 subtract 4, so that's going to be -7, like that. So we've now got ourselves the displacement vector from C to D as requested by the first part of the question. It then says hence, so that means use your previous part of your working. Find the distance between the point C and the point D. Well, if we know the vector going from C to D, which we know here, then all we need to do is calculate the magnitude of this vector, and it's going to tell us the distance between the 2 points. So the distance is going to be the magnitude of 9, -7, which is going to be equal to the square root of our horizontal component squared plus our vertical component squared, like that. Make sure you put negative numbers in brackets if you're going to square them. And then you can pop that in the calculator or calculate it manually. And I believe that we get the square root of, and it would be 81 plus 49, which gives me 130. Then just check, can I simplify my third? I don't think I can. So that means the final distance between point C and D can be given as the square root of 130. Now let's have a look at another application of our displacement vectors. So we've got O to H, the position vector of H, which is 2a subtract 5b. So A is in bold and B is in bold because they are vectors. Now, I don't know the specific column vectors for them, but it's actually not relevant to the question. We then got the position vector of G, O to G, and that is equal to 4 lots of A subtract 2 lots of B, where A and B are in bold because vectors, whereas the 4 and 2 are not in bold because they're scalars. We need to find the displacement vector G to H in terms of A and B. So if I want G to H, that is going to be equal to the position vector of our destination, so O to H, subtract the position vector of our start point, so that's going to be O to G, like that. So I'm going to substitute in my vectors for both of these. So for O to H, it is 2a subtract 5b. And I'm going to underline my vectors because I can't write in bold. And then we've got subtract. And then we've got O to G, which is our other vector here. So in brackets, I'm going to put 4a subtract 2b. Make sure you've definitely got brackets there because you're going to be subtracting multiple terms. So then let's simplify this. We have 2a subtract 4a, so that's going to give me negative 2a, like that. And then we've got negative 5b subtract negative 2b, so that's going to be addition. So negative 5b plus 2b gives me negative 3b, like that. And that would be my final answer for G to H. Let's look at another application of our displacement vectors. So we got ourselves a geometrical problem. We're told that ABCD is a parallelogram. So remember, in a parallelogram, the opposite sides are parallel and they're equal in length. Now we're told the displacement vector from A to B is negative 2, 3. So let's just indicate this very clearly on my diagram. Okay, so A to B would be along this line here going in that direction. And the vector is negative 2, 3, like that. Okay, and then we're told that A to D is 3, 5. Okay, so A to D would be this line here joining up A and D going in that direction of the arrow. And the vector is 3 to 5. So that's how we get from A to D. Now, given this is a parallelogram, so the opposite sides are equal in length and they are parallel, that means the vector from A to D is going to be the same as the vector from B to C due to the fact that they're the same length and they are parallel. So I know that B to C is going to be 3 to 5, like that. And if A to B is negative 2, 3, then D to C in that direction would be negative 2, 3 as well. So we've got vectors for all the side lengths. Now let's start thinking about coordinates. So we're given that the coordinates of A are 3, 1. So I'm just going to mark that on my diagram. So if you want to write out the position vector, you could. And then we need to find the coordinates of B, C, and D, the other vertices of my parallelogram. So if we're starting at A, because that's the point we actually have coordinates of currently, if I wanted to get the coordinates of the point B, so let's start with that, okay, which is this point here, I would need to know how we get from A to B. Because if I knew how I got from A to B, I could add that onto the coordinates of A, and then I'd have the coordinates of B. Well, the coordinates of A are 3, 1, and how we get from A to B, well, that's negative 2, 3. That's 2 to the left and 3 up. All I need to do is add those values onto my coordinates, and I'll have the coordinates of B. So we're doing negative 2 in the x direction. Okay, so we're going to subtract 2. So that is going to give me 1. And then in the y direction, in the vertical direction, we're going to be doing 3 up. So we're adding 3 to our y coordinate. So that is going to give me 4. So the coordinates of B would be 1, 4, like that. So now let's move on to the coordinates of C. So if we look at what we've now got the coordinates of the point B, which I'll just circle here again. We need to end up at the coordinates of the point C. So if I know the coordinates of B, which are 1, 4, if I knew the vector from B to C, I could then add that on to get the coordinates of C. Well, we know that vector, it is 3, 5. So all I need to do is take the coordinates of B, 1, 4, and I'm going to add on 3 to my x coordinate, which I'm going to indicate here. So that is going to give me 4. And I need to add on 5 to my y coordinate. So if I add that on, I am going to get 9. So the coordinates of C would be 4, 9. So now let's move on to D, which is my final point. So we know the coordinates of the point C. What could I do with that to get to the point D? Well, I need to know the vector from C to D. Currently, I know the vector going from D to C because that's the direction of the arrow. So D to C would be the vector negative 2, 3. If I want to go from C to D, that is the return vector. So I need to multiply by negative 1. So we would get positive 2, negative 3. And now we know how to get from C to D. I need to add on 2 to my x coordinate, which I'm going to do down here, which would give me 6. And then I need to subtract 3 from my y coordinate. So that is going to give me 6 as well. And that will be my coordinates of D, like that. So just be careful on the direction of the vectors, you know. Now, an alternative way to do the point D would be to use the point A and then add on the vector 3, 5, which is the vector from A to D, and you should still get the same answer, because if you do the 3 plus the 3, you get 6. If you do the 1 here plus the 5, you also get 6, which is the same as what I ended up with for B. So we're now going to look at an application of column vectors and displacement vectors within another topic you need to be familiar with. And the topic in question is transformations. So we need to describe the transformation from shape A to shape B. Okay, so let's first just identify shape A, which is this one here, and then shape B, which is this one down here. Now, transformations, there are 4 transformations you should be familiar with. So we got rotations, reflections, enlargements, and translations. So we need to figure out which of the 4 transformations is this one. Well, clearly the shape has not been spun around, it's not been rotated, it's clearly not been reflected, it hasn't changed in size, so it's not an enlargement. So that leaves us with a translation. So I'm going to start by writing translation here. And a translation is where we move an object to the left or to the right and up or down. So let's figure out how much to the left or right and how much up or down. To do this, we're going to take 2 corresponding vertices of the shapes. So for shape A, I'm going to consider this vertex down here, and then the corresponding vertex will be this one here. Essentially the same vertex on the other shape. Now let's figure out how I get from A to B. Well, I'd have to go 4 to the right, and then I'd have to go 3 down. So 4 to the right and 3 down. Well, how could I describe that movement? How could I write it out on my page? Well, we could use a column vector. I would say that this is a translation by, and then write my column vector. So it's 4 to the right. So positive 4 is our horizontal component, and then it's 3 down. So negative 3 would be my vertical component. So that would be the answer to the first question. And that movement for negative 3 should work for any pair of corresponding vertices. So if we took the vertex at the top here and the vertex at the top for B, well, if I went 4 to the right and then 3 down, you can see I end up on that vertex. So let's move on to our second question. So we're going from shape G to shape C. So G is our start point down here and C is our end point. Now, clearly, once again, it hasn't been rotated, it hasn't been reflected, it hasn't been enlarged. So it's going to be a translation again, and that's where our vectors come into play. So I'm going to write translation by, and we're now going to have to figure out my vector. So let's take a point on G. So I'm going to take this point down here, and then the corresponding point on C would be here. So starting at G, we'd have to go upwards like this. Okay, so I've gone 7 upwards in total, and then we're going 1 to the left. Like that. So my vector is 1 to the left, which is negative 1 for my horizontal component, and we've gone up 7, so my vertical component would be 7 like that. So when you're describing translations, you need to use a vector. So we're now going to look at some more geometrical problems involving algebraic vectors. So we have a diagram here, and we're told some vectors on the diagram. For example, we're told to get from K to L, the vector in question is equal to A. And of course, I'm going to underline it because it's a vector. Then we know how to get from L to M. L to M would be the vector that's equal to B. And then N to M would be the vector 3A. So I could write all of those out if I wanted to, but you can see them on the diagram. Of course, we also know the return vectors. So for example, if K to L is A, then L to K, well, we just have to multiply by negative 1. And we would get the return vector, which would be negative A like that. And we could do the same for L to M and N to M. Now, in terms of what shape this is, well, K to L must be parallel to N to M, since the vector here is A, vector here is 3A, so they're scalar multiples of each other. So this should be a trapezium. Perhaps in some problems, you might need to use properties of specific shapes. But let's get into the main part of the question. We need to write the following vectors in terms of A and or B. Okay, so we're starting with M to K. So I'm going to write M to K here. Now, the first thing I'm going to do is just map out my path from M to K using my vertices, using the capital letters. Now, the side lengths I'll be traveling along are going to be the ones with the arrows on them. Okay, so for example, between K and N, we currently don't have anything there, so we have to consider the other side lengths and whether they have arrows on them to indicate vectors. So if we're starting at M and we need to make our way to K, well, where could I go from M that's going to get me going towards K? Well, I could start by going to L. So I could start by doing M to L. So that's going to be my first movement. Then once I'm at L, can I get to K? Yes, I can, because I have a vector on that side. So what I would want to do is do M to L, which I've written out here, followed by L to K. So I'm going to add on L to K because I want to work out the resultant of those two vectors, which is going to give me M to K. So let's fill in the vectors in terms of A and B, because that's what the question asks for. Well, M to L, if we look at the line with M to L, we got the vector B on it. However, look at the way the arrow is going. That's going from L to M. So if I want to reverse it, I need to multiply by -1. So it's going to be negative B. Now I'm at L and I'm doing L to K. Well, what's the vector L to K? Well, I know K to L is A. So L to K must be negative A because it's going in the reverse direction. So that there would be the vector for M to K. That will be my final answer to part A of my questions. Now let's look at N to L instead. So I'm going to start by identifying where N and L are on my diagram. So we got L indicated there, so I'm just going to indicate N. And I have to get from N to L. So we need to start thinking about where we could go first. Well, we can't go up to K, so we're going to have to go along to M. So I'm going to start by doing N to M. And then once I'm at M, can I get to L? Yes, I can. So I'm going to add on M to L, like that. Now let's replace both of these with their vectors in terms of A and B. So N to M is 3A. And then M to L is the reverse direction of L to M. So it's not going to be B, it's going to be negative B, like that. And that would be my final answer for N to L. Now let's have a look at N to K, which is my next question. So I'm going to write N to K. And then let's start by labeling N and K on my diagram. So we got N already labeled, and then K is going to be the point up the top here, which I'll put on in green. So we need to get all the way around from N to K. So we can't go directly from N to K. So we're going to start by going from N to M because I know the vector there. Okay, so let's map out my path. We're going from N to M. And then from M, I could go to L next, okay, on my path. So I'm going to add on M to L. And then once I'm at L, well, can I get to K? Yes, I can, because I got a vector of that side length. So then I am going to add on L to K, and I'm at my destination. So now let's replace these vectors I've got written here in terms of A and B. So N to M is 3A. M to L would be negative B because we're going against the arrow. And then L to K would be negative A because once again we're going against the arrow. Now this wouldn't be our complete final answer because we should simplify, collect our like terms. Well, we've got 3A and a negative A, so that is going to make 2A. So I'd write 2A and then subtract B like that. Okay, now let's do K to N. Okay, now K to N should be fairly straightforward because that is the reverse direction of N to K. So that is going to be equal to -1 multiplied by N to K. So I'm going to take my vector for N to K and I'm going to multiply by -1. So we get -1 times 2A, subtract B. And if I expand my brackets, I would get -2A, and then it's going to be plus B like that. So that would be my final answer. Now let's have a look at a different geometrical problem. So here we have a parallelogram A, B, C, and D, which are my vertices. And we're told that AB is parallel to DC and AD is parallel to BC. Okay, because of course it's a parallelogram. Now I can add on some extra vectors here. Because this is a parallelogram, the opposite sides are the same direction and they're equal in length. Therefore, the vectors on the opposite sides should be the same. So if A to B is equal to P up here, then D to C is also going to be equal to P. Now, if A to D is equal to Q, then B to C is also going to be equal to Q as well. So I've now got vectors for all the side lengths, which is quite convenient. So we've used properties of shapes here, which will come into play regularly in these types of questions. We now need to express in terms of P and Q, A to C. Okay, so let's start with A to C. So we're beginning at A, so we need to identify A, and we're ending at C, so I need to identify C. And we need to think, how can we get there? And in this question, we can use any side length because we got the vector on any side length, which is quite convenient. So if we're starting at A, we have a couple of options. We could either go to B or we could go to D. And I think either will work. So let's go from A down to D as my start point. And then can I get from D to C, which is my destination? Yes, I can. So I'm going to add on D to C like that. And now what I need to do, because I've ended up at C, I need to replace both of these in terms of P and Q. So A to D was the vector Q, and then D to C was the vector P. So we're going to plus P to get the resultant, and that is my final answer. Now let's look at B to D, which is the second part of this question. So if we're starting at B, let's just indicate where that is. So that is over here, and then D is down here. So if we're at B, where could we potentially head first? Well, we could go to A, or we could go to C. So let's go down to C. I don't think it's going to matter which way in this case because we have the vectors for all the side lengths. So we're starting by doing B to C. Then once we're at C, can I get my way to D? Yes, I can. I've got the vector on that side length, so I need to add on C to D. So let's fill in my vectors in terms of P and Q. So B to C is this vector here. It's positive Q. And then C to D, well, that goes against the arrow, so it's not P. It's going to be negative P, like that. And that would be my final answer. Let's have a look at another problem. So once again here, we've got a parallelogram, but it's looking a little bit more detailed because we've now got the diagonals of our parallelogram drawn in. So my diagonals would be A to C and D to B. Okay, so they cross over each other at T. Now, because it's a parallelogram, what I'm going to do is just annotate on those extra vectors I know. If A to B is P, then D to C we know is P because they're opposite sides in a parallelogram of the same length and by the same direction. And then if A to D is Q, then B to C is also Q like that. Now what we need to do is express A to T in terms of P and Q. So I need to get from A to T here. So the question is, how am I going to do that? Because I don't have any vectors joining up to T currently. Well, we're going to have to use properties of a parallelogram, okay? Because in a parallelogram, the diagonals of a parallelogram, they bisect each other. Now, if they bisect each other, that means they cut each other in half. Therefore, T here is the midpoint of the diagonals. And this is a key fact that we're going to use. Because if it's the midpoint, that means if I knew how to get from A to C, well, A to T is just going to be half of that movement. So the goal here is to calculate A to C, and then we can halve it because T is going to be the midpoint of that line. So what I'm going to write out is that A to T is equal to half of A to C. And now we need to figure out what A to C is going to be. So I'm going to write a half, and let's map out my route from A to C. Well, if I'm starting at A, and I need to end up at C, I could go down to D first, so it'd be A to D. And then we could go across from D to C, so I'm going to add on D to C like that. And that will be my vector for A to C. So now let's fill in my P's and Q's. So for the vector A to D, that is Q. For the vector D to C, that is P. And in both cases, we're going with the arrows, so they're both going to be positive. And then I've got myself the vector for A to T. I can leave it like that, or if you wanted to, you could expand the brackets. Either way is sufficient. Now let's look at a slightly more complicated problem involving a different shape. So here we have a regular hexagon, and we've got our 6 vertices labelled as O, A, B, C, D, and E. So O should be our origin. Now we're told that O to A is equal to A, so that's indicated on my diagram, and O to E is E, and that is also indicated on my diagram. Now we need to find the following vectors in terms of A and E, but before I do that, I just want to go to my diagram and annotate on any other vectors I do know. So this is a regular hexagon. So if we start thinking about a regular hexagon and the relationship between all of these blue lines and the triangles I've got there, around the middle of my regular hexagon, I have 1, 2, 3, 4, 5, 6 angles. Okay, and all these angles should be the same because this is a regular hexagon. So the angles around the point add up to 360, and there's 6 angles. So if we divide by 6, I get 60 degrees like that. So I know, I'm just going to put it in for one angle, this is 60 degrees. So because this is a regular hexagon, I know that the side length from D up here to my midpoint is equal in length to my side length from my midpoint to C. So therefore this length here is the same as that length there. So that means I have an isosceles triangle, and I know the apex angle is 60. So we can calculate my base angles, which should be the same size as each other. The calculation that I'm going to end up doing is 180, subtract the 60 degrees, and then we're going to divide by 2. So that is going to give me 120 divided by 2, which is 60 degrees as well. So they are all 60 degrees. Therefore, these are all equilateral triangles. So all the angles inside my shape split up by the blue lines are going to be 60 degrees. So for example, this would be 60, this would be 60, and so on like that. I'm not going to fill them all in. Now, because all the angles are 60, that means we have equilateral triangles. So therefore, the side lengths on my regular hexagon, which are all the same length, should also be equal to those other lengths I've annotated there from the midpoint to D and the midpoint to C, like that. Okay, so all these side lengths are equal. Now, what this means is we can fill in some extra additional vectors. So I am just going to declutter my diagram and rub these off, just because we know everything's going to be 60 degrees and we know all our side lengths are equal. So if we look at the vector from O to E, this vector here is going to be equal to this vector here going from the midpoint, which I'm going to call M, to D, because that blue dotted line between them is the same length and it's inclined at the same angle, so they should be parallel to each other. So if they're the same length and they're parallel, they're going to be equal to each other. We can also fill in some other vectors. We can fill in from A to M. This here is going to be E. And then for similar reasons, if O to A is equal to A, then M to B will also be equal to A, and E to M will also be equal to A, like that. And then there's a couple of other vectors I've actually missed. Okay, from B to C, this would be equal to E, okay, because it's the same direction. And then also D to C would be equal to A. So I managed to fill in a lot of vectors in my diagram that we can make use of. Now let's have a go at finding the vectors that I've been asked to find. So let's start with the position vector of B. So position vectors always start at the origin. So they're going from O to B. So I need to think, how do I get from this point O to this point B using the vectors I have written there? Well, we could start by going from O to A, because I know this vector here is A. And then once I'm at A, we can go inwards to M, because I can't go directly to B because I don't know that vector there. Okay, so I'm going to want to do E, so I'm going to add on E. And then once I'm at M, I can then go along A to get to B. So I'm going to add on this A here. And then if we simplify, I get 2A plus E, which is my final answer. Now let's have a go at the position vector of C. So that's O to C. So I'm just going to start by indicating on my start point and my end point. So starting at O and we're ending up at C. Now to go from there to there, we don't have the vectors directly across the middle, so we're going to have to make a bit of a detour. But let's see if we can make use of my previous part. If we're starting at O, well, we could start by going to B, because I know the vector for O to B. I just figured what that was, so I'm going to write O to B here. And then once I'm at B, well, then I just need to add on this E to get to C. And that will give me my final answer. So all I need to do to get my final answer is replace O to B with the 2A plus E that I figured out here. So I'd write 2A plus E, and then we're going to add on this additional E. And if we simplify that, I get 2a plus, and it's going to be 2e like that. Okay, and that will be my final answer to that one. Now let's do O to D, which is the position vector of D, because that's what I'm being asked for next. So let's just identify my start point and my end point. So we're starting at O, and we're ending up at D over here. So this time we're sort of going upwards instead. So if I just write O to D here, I might want to start by going from O to E potentially, or potentially a quicker way of thinking about things is I know what O to C is. Okay, I just did that in the previous part. So I could say that this is equal to O to C, and then in order to get from C to D, I have to go against this vector here. So I'm going to want to do negative A like that. Okay, so this is equal to O to C, which is this vector over here, be 2A plus 2E. And then I am going to subtract off the A here. Now, if we simplify this, 2A subtract A is 1A. So we get 1A plus 2E as my final answer. And that was probably quicker than going through each vertex individually. So do always be on the lookout and see if you can use the previous part of the question to assist you. Now let's look at part D, which is the position vector of the midpoint of AB. Now the midpoint of AB is not indicated on my diagram. So I am going to start by putting it on my diagram. So I am going to put a dot here at the midpoint, and let's label it letter. Well, the next letter not used is F. So in part D, we need to find O to F. That is my goal here. So if we're O, what could I potentially try and do first? Well, I could go down to A. So I could make my way down here using this vector. So I'm going to write in an A. And in order to get from A to F, okay, well, F is the midpoint of A to B. Therefore, I would need to find A to B and half it and add that on. So we need to add on half of A to B. So let's go and calculate what A to B is. So let's just write out what I've already got here. And then to get from A to B, well, I might want to go to M first. So we're going to go E. And then once I'm at M, I can go along the vector A to get to B. So I'm going to add on A like that. And then we can simplify what's written there. We can expand the bracket. So A plus a half E plus a half A. And if we have 1A plus a half A, well, that's going to be 1.5 A, or in other words, 3 over 2A. And then we have to add on our half of E. Let's now have a look at our final part. So we need the position vector of the midpoint of BC. So is the midpoint of BC indicated on my diagram? No, it's not. So I'm just going to put a dot here, and let's use the letter G. So this part of the question is asking me to find the position vector of O to G like this. So what I might start by thinking is, can I use any of my previous working? Do I know how to get close to G? Well, I know the position vector of point B. Okay, so I can start by writing in O to B to get us close. And then in order to get to G, well, that's the midpoint of B to C. So I need to find B to C and half it. So I need to add on half of B to C. Now the vector O to B, well, I found that earlier on, it's the 2A plus E. So I'm going to write that in here. And then do we know B to C? Yes, we do. It is the vector E. So we just need to add on half of E like that. And then all we need to do is simplify what's written here. So we got 2A, that's going to stay the same. And then 1E plus half E, well, that gives me 3 over 2E. So that would be my final answer. We're now going to look at a question involving ratio. So we have a diagram, and the vectors A to B, which is 3A, is indicated on the diagram. And then A to C is equal to 4B, which is also indicated on the diagram. Now we're told about this point D, which lies on the line BC. So that is indicated on my diagram. If it wasn't, make sure you draw it on. And we're told that B to D to D to C is the ratio 1 to 3. Okay, so I just want to think about that and what we know about the line and the point D. Well, this ratio here, splits up the line going from B to C. Okay, so that's going to be this line here. What I want to think about is what fraction of the line is just between the B and the D, and what fraction of the line is just between the D and the C. So we're going to have to make use of the ratio. So in total here, for the line B to C, this is splitting it up into 4 parts in total. 1 part plus 3 parts gives me 4 parts. So I have 4 parts along my entire line. So if I was to indicate my entire line over here, okay, that is 4 parts. Then between B to D specifically, that is the 1 part in my ratio. So I have 1 part here. Then between the D to C, I have 3 parts, so I have 3 parts over here. What we can now do is write my ratio as fractions. Between B to D, I have 1 part out of a total of 4 parts, so I have 1/4 of my line between B to D. And then if we consider D to C instead, well, for D to C, we have 3 parts out of a total of 4 parts. So therefore, between D to C, there is 3/4 of the line of B to C. Okay, it's very important to turn our ratio into fractions because fractions are going to be far easier to use when we actually try and do the vector part of the question. So I'm just going to take off all of these parts up here. And now we've got that 1/4 and 3/4 there. Now, why are they useful? Because if I knew what the vector to get from B all the way to C was, well, then the vector from just B to D, that's going to be 1/4 of that. Or the vector from just D to C is going to be 3/4 of B to C. So it allows us to find other vectors that aren't explicitly going to be written there. So now let's have a go at actually answering the question that we've been given. So we are told to write the vector A to D in terms of A and B. So let's just identify where is A and where is D. So that is this point here. So we need to think about how I'm going to get from my start point A to my end point D. So what I'm going to do is write out my path. So if we are doing A to D, we're starting at A. Well, where could we head first? We have a couple of options. We could go from A to B, or we could go from A to C. Either way could potentially work, I think, given what we've got in this question. So let's just start by going from A to B. So I'm going to write out A to B here. And then once I'm at B, which I'm going to indicate in red, I want to get to D. Now, as you can see, there is no vector currently written on there, but I'm going to start by writing plus B to D here. And we need to think about how we're going to obtain B to D. Well, for the vector B to D, that is going to be 1/4 of the vector from B to C, which might be a bit more easy to calculate because both the B and the C are vertices of my entire shape. Okay, so what I can say is that B to D is equal to 1/4 of B to C. And I need to find B to C and multiply by 1/4. So let's start filling in my vectors in terms of A and B. So the vector A to B is the vector 3A, because that goes with the arrow, so it remains positive. So I've got that there. And then the vector B to C, well, let's think about how we're going to find that. Okay, so if I'm at B and I want to get to C, well, what I could do is first go down to A, so we'd do negative 3A. And then we'd be at A, and once we're at A, we'd have to do positive 4B in order to get to C. So we're going to add 4B on like that. So that would be the vector from B to C. Now what I can do is I've got everything in terms of the lowercase a, lowercase b, our vectors A and B. We can now expand the brackets and simplify. We got the 3A, and then we got 1/4 multiplying the bracket. So that would give me 1/4 times negative 3A would be negative 3/4 of A. And then we got the 1/4 multiplying the positive 4B. So that's going to be positive 1B. Now that we've expanded, we can simplify. So if we've got 3A, subtract 3/4 of A. So we need to do 3 subtract the 3/4. So 3 as a fraction with a denominator of 4 would be 12 over 4 because that's equal to 3. And then we're going to subtract 3/4. So we're going to end up with 9/4 in total. So we've got 9/4 of A, and then we've got the plus B there. And that would be my final answer for A to D. We're now going to look at a harder question involving ratios. So we've got here that OACB, our big shape, is a quadrilateral. And we're also told that ABB, so this line here, and OPC, which is this line here, are straight lines. We're then given three vectors down here, which are all annotated on my diagram. Then we're told a ratio. So it's the ratio from O to P to P to C. So O to P is this part here, and then P to C is this part here. Therefore, this ratio splits up the line going from O to C. So what I want to start is turn this ratio into a fraction. Okay, I want to figure out what fraction of that line, O to C, is between O and P, and what fraction is between P and C. So if we look at my ratio, we have 2 parts to 3 parts, so we have a total of 5 parts. Now, if we have 5 parts in total, then that means between O and P, we have got 2 parts, so a fraction of 2/5 of the line is between O and P. So I can put a 2/5 over here. Now, my 2 fractions should add to 1, so my other fraction should be 3/5. Therefore, between P and C, there's 3/5 of that line. So what this means is, if I could figure out the vector going from O to C, for example, okay, the vector going from just O to P would be 2/5 of that. Okay, so that's quite a handy bit of information that we've got there. We then need to work out the ratio of A to P to P to B. And in this case, we don't have the arrows above the letters, okay, because this is not referring to the vectors specifically. This is referring to the length A to P and the length P to B. However, we can find the vectors A to P and P to B in order to help us get this ratio. So in this question, step 1 is going to be to find A to P. Step 2 is going to be to find P to B. And then step 3 is going to be to write our ratio. So let's start with finding A to P. So I'm going to write A to P up here. So we're starting at A, and we need to end up at P in the middle here. So where could we go from A? Because I don't have any information about A to P or A to B in that direction, so we can't go along that line. So we're going to have to go somewhere else. Well, I don't know how to get from A to C. So really our only option is to go from A to O. So I'm going to start by going from A to O like that. Now I'll be at O. And do we have any information about how we can get to P from there? Well, we do have this fraction here, which we could potentially make use of. So I think we can get directly from O to P. So I'm going to add on O to P. Now A to O would be the reverse of this vector here. So instead of being positive 3a, that's going to be negative 3a because we're going against the arrow. Now O to P, we don't have the vector written on our diagram. However, this 2/5 means the vector O to P is going to be 2/5 of the vector all the way from O to C. So if I can figure out O to C, I can multiply by 2/5 and I'll get O to P. So what I can write is that O to P here is equal to 2/5 of O to C. So let's now have a go at finding O to C. So I'm just going to write in the information I have got so far. Now, if we're starting at O, so our green point here, and our end result, we need to get to C. Well, we could go around the outside to B, and then from B to C. Okay, so to work out O to C, what I'm going to do is I'm going to go from O to B, and then I'm going to go from B to C. So I need to add that on. So now let's calculate what we got in our bracket in terms of the A's and B's. So we'd have negative 3a plus 2/5 of, and O to B is 6b, and we're going with the arrow so it remains positive. And then B to C is the 5a subtract b. So I'm going to add that on, plus 5a, and then subtract b like that. Now let's simplify my bracket. So we'd have 2/5 outside, and then inside it we got 6b, subtract b, so that's going to give me 5b, and then we've got plus 5a like that. Now let's go further and expand the bracket, because I want to simplify with the negative 3a as well. So we've got negative 3a, and then we're going to multiply both terms in the bracket by 2/5. So if we start with the first term, well, multiplying by 2/5 means divide by 5 and then multiply by 2. So if we go to this 5 and we divide by 5, we get 1. If we multiply by 2, we're going to get 2. So that's going to give me 2b. And then for my next term in the bracket, well, if I divide by 5, I get 1a times 2, we get 2a, like that. Then simplifying further, we end up with negative 3a plus 2a gives me negative 1a. So I'm going to write negative a, and then that's plus 2b. So we've successfully found a vector, which is a 2p. So I'm going to circle that because that's the key bit of information I need in order to be able to answer the question. Now what we need to do next is move on to step 2, which is finding p to b, because step 1 was done here. Now let's do step 2, which is to find the vector from p to b. So I write 2 here, and I'm going to write p to b like this. So we're starting at p, which I'll leave written in red. And then we need to end up with b up here, making use of my vectors. So where could we head first? Well, what we could do, because we don't know how to get directly from p to b, what we could do is go from p down to o. And the reason I'm going to do that as my start point is because we've already found the vector o to p in the previous part that we are working on. Okay, if we look up here, we were working with o to p, and that was 2/5 of o to c, and that was 2/5 of o to b plus b to c. So that vector would be this one here, and then we've got the simplified version in the bracket below that. So this is the one I'm going to use because this vector here is o to p. So if I want p to o, I'm going to have to multiply that vector by -1. Okay, so we're going to make use of that. But once we're at o, then can we get directly to b? Yes, we can, because we've got the vector on this side length, so I can add on o to b like that. Okay, so let's write in my vectors in terms of a and b. So p to o is going to be o to p multiplied by -1. So I'm going to put a negative sign in front of the 2/5. So we'd have negative 2/5 multiplied by 5b plus 5a, like that. And then o to b is the vector 6b, so I need to add that one as well, like that. Now let's expand the brackets and simplify, and we already know what we're going to get from our brackets if we are multiplying by positive 2/5. So really the only change is the sign of those two terms are going to change. We're going to get negative 2b, subtract 2a, and then we're going to add 6b. Now if we simplify, negative 2b plus 6b, well that gives me positive 4b, and then we've got the subtract 2a there. So I've successfully found a vector from p to b in its most simple form. So I'm just going to write p to b here so it's clear, and then let's circle that in red. So we've now completed step 2. So step 1's done, step 2's done. We now need to move on to step 3, which is actually giving the final answer of the question. So if I write my two vectors over here, we were looking at a to p, which has come out as negative a plus 2b. And then we've got p to b, which has come out as 4b subtract 2a. So what we need to think about is what is the relationship between these vectors, because I need the ratio of the lengths of them. So I'm just going to write a to p to b. So if we look at a to p, we've got a negative a here, but then in p to b, we've got negative 2a. So we'd have to multiply by 2 there. So let's then check, does that work out for our b's? Well, if I go to my 2b and I was to multiply by 2, would I get 4b? Yes, I would. Okay, therefore p to b is twice as big as a to p. So my ratio is going to be 1 to 2 with the 2 as the p to b. And that would be my final answer. We're now going to look at how we can prove vectors are parallel in geometrical problems involving algebraic vectors. So from earlier in the video, we know that vectors are parallel if one is a scalar multiple of the other, and that a negative multiple is absolutely fine. So what we're going to think about is which of these vectors here are parallel. So let's compare the a to b and the c to d, and we need to determine whether they're scalar multiples of each other. So to get from 4a to 8a, you'd have to multiply by 2. Now if I was to go to the negative 2b and multiply by 2, would I get 12b? No, you wouldn't. Okay, you'd have to multiply by negative 6 instead. Therefore, these vectors are not scalar multiples of each other, because if they were scalar multiples, these values would be the same. So A to B and C to D are not parallel. Okay, so I'm just going to take off my working there, and we're going to consider C to D and E to F instead. Okay, so how do I get from 8A to 8A? Well, I'd have to multiply by 1. Now, if I was to take the 12B and multiply by 1, would I get negative 4B? Clearly not. You'd have to multiply by negative a third. Therefore, these two vectors are not scalar multiples because these numbers are not the same, so they are not parallel to each other. So we got one more combination to try. Okay, we are now going to compare the A to B with the E to F. Well, how do I get from 4A to 8A? Well, you'd have to multiply by 2. Now, if I took the negative 2B and multiplied by 2, would I get negative 4B? Yes, I would. Okay, it would be the same value I'd have to multiply for the A's as I'd have to multiply for the B's. Therefore, we can conclude that A to B and E to F are parallel. However, we do need to write our working out in a very specific way. So what I'm going to do is I'm going to write this vector E to F over here. So E to F is equal to 8A subtract 4B. Now, in order to show that this is definitely parallel to the A to B, what I'm going to do is factorize the E to F. And in my bracket, when I factorize, it's going to be the vector A to B. So it's going to be 4A subtract 2B. So I'm going to write 4A subtract 2B in my bracket. And I just need to decide what number needs to go out here to make this statement down here the same as the statement above it. Well, I know what that number should be. It should be these 2's that I've got here. So I need to put a 2 in front of my bracket. And now that statement is correct. E to F would be equal to this down here. Now what I'm going to do next is replace my bracket, because my bracket 4A take 2B is equal to A to B, which we've got from that statement there. So I can write in place of that bracket A to B like this. So what I've essentially concluded is that E to F is equal to 2 lots of A to B. So now I can write a conclusion. I can say, therefore, E to F is a scalar multiple of A to B. So E to F and A to B are parallel. And that is the type of working that is expected. So now let's have a look at a geometrical problem where we're going to put this to use. So we've got a diagram and it shows the vectors A to E, which is indicated here, and then D to C is indicated down there. Now it says that the points E and B are midpoints of AD and AC respectively. So let's just think about that. So the point E is the midpoint of A to D. Okay, so can we figure out any other vectors based off this? Well, if it's the midpoint of A to D, then if the vector A to E is 3A take 2B, then the vector from E to D should also be 3A take 2B as well. So I've got another vector onto my diagram there. Now let's consider B. So B is the midpoint of A to C, which is over here. Now, can I figure out any other vectors? I don't think so, because I don't actually know a vector between A to C or A to B or B to C at the moment. But if B is the midpoint, then if I was able to figure out the vector from A to C, for example, if I was to halve that vector, that would give me the vector from A to B. So that's quite a key bit of information that we might have to make use of later on. Now let's look at what we're actually being asked to do. So we need to determine if D to C and E to B are parallel. So there's sort of two main steps we need to do here. We need to find both of these vectors. So we need to find D to C. And then after I've done that, I need to find E to B. And then we can think about whether they're parallel or not. Okay, so let's start with number 1, which is D to C. Now, if we look at the question, they've actually given us D to C. It's this vector here. It's 2A plus 4B. So that means number 1, step 1 is already done. It's given in the question. That won't always be the case, but it is with this one. Now let's move on to step 2, which is finding E to B. So I'm going to write E to B here. And let's identify our start point, which is already in red, it's E, and our end point, which is already in red, it's B. Okay, and I need to map out my path. How am I going to get from E to B? Well, what I could start by doing is go from E to A or E to D, because I don't know a direct route from E to B. So it's up to you which one you do. Let's just go with the arrows. So let's go for E to D, like that. Then once we're at D, well, I don't really have a choice other than going to C now, because I don't want to go back to E. Okay, so then we're going to go to C. So we're going to add on D to C, and we know that vector as well. Now we're at C. Ideally, I want to get to B. Okay, so I want to add on C to B. Now, the issue is I don't currently know the vector C to B, so we're going to have to think about how we're going to obtain that. So let's just start filling in what we know in terms of the lowercase a's and the lowercase b's are vectors. So E to D is the vector 3a take 2b. So I'm going to put that in. And then the vector D to C, well, that would be the 2a plus 4b, like that. Now, vector C to B, that's going to be the problem one. So now we have to use the fact that B is the midpoint of A to C. Because if I was able to figure out how I get from C to A, I could then halve that movement, and that's going to give me the vector from C to B. So what I'm going to say is the vector C to B is equal to 1/2 of C to A. And we need to calculate what C to A actually is. Okay, so let's simplify what I've got so far. So 3a plus 2a gives me 5a. Negative 2b plus 4b gives me positive 2b. And then we need to calculate half of C to A. So let's write in my half so we don't forget it. And an open bracket. Now let's think about how I'm going to get from C to A using the vectors written on my sides. Now I can't go in the direction of B because we don't know a vector across that line. So what I'm going to have to do is I'm going to have to head to D first. Okay, so I'm going to have to do C to D. So then once I'm at D, I'm then going to have to head upwards to E, okay, which I do have the vector of. So I'm going to add on D to E. And then once I'm at E, I'm going to have to head up to A. I know the vector from E to A, so I can add on E to A, like that. Okay, and that's going to get me all the way from C to A. So now let's replace all of those vectors and write them in terms of A and B. So we'd have the 5a plus 2b from before, and then we got the half in front of the bracket. So C to D, that goes against the arrow here. Okay, so we're going to have to do the negative of this vector. So we're going to multiply that by -1 to get negative 2a, take away 4b. Then to do D to E next, well, once again, we're going to be going against the arrow. So we're going to have to multiply this vector by -1. So it's going to become a negative 3a. And then because it's originally negative 2b, it's going to become positive 2b. And then we're at E, so then we need E to A. Well, E to A is going to be this vector here. And once again, we're against the arrow, so we're going to have to multiply by -1. And actually, that vector is going to be the same one as I've just written out, because E was midpoint there. So I'm just going to subtract another 3a from here, and then add another 2b from there. Okay, and then close bracket. And then we have all the information there to hopefully get a simplified form for E to B. So I'm first going to simplify inside my bracket. So I'd have my half outside, and then we got negative 2a, subtract 3a, subtract 3a. So that's going to be negative 8a. And then if we do my b's, we got negative 4b plus 2b plus 2b. So that's actually going to come out as 0b, which is quite nice for simplifying. Now let's multiply by a half. So we'd have 5a plus 2b, and then a half of negative 8a is negative 4a. And then collecting my like terms, 5a subtract 4a is positive 1a. And then we got the plus 2b like that. And that is my vector for E to B. Now what we need to do is compare this vector to D to C. So I'm just going to write D to C down at the bottom here, just for reference. So D to C is equal to 2a plus 4b. Now let's investigate, are they scalar multiples of each other? Because remember, we're trying to determine if they are parallel. So we need to use our definition of parallel vectors, which is about them being scalar multiples. Well, to get from 1a to 2a, we'd have to multiply by 2. To get from 2b to 4b, we'd have to multiply by 2 as well. So they are scalar multiples. They are going to be parallel. So what I'm going to do is I'm going to factorize the d to c. And in my bracket is going to be a plus 2b, because that's the vector I'm trying to show it's a scalar multiple of. So my bracket's going to be a plus 2b. Then we just need to figure out what goes in front. Well, that's going to be the number we're multiplying by here, so the times 2. So I'm going to put 2 in front like that, and then close my bracket. And then this vector here is just equal to e to b, so I'm going to replace it with e to b. So we get 2 lots of e to b. So what I've established is that d to c is equal to 2 lots of e to b. So we've concluded and shown conclusively they're scalar multiples, so we can make our conclusion. Therefore, d to c is a scalar multiple of e to b. So they are parallel. And that is a complete proof. We're going to look at how we can show that 3 points form a straight line using vectors. So let's consider 3 points. So I'm going to call this point here, we'll call it A. Then this point here, we'll call it B. And then this point over here, we'll call it C. Like that. Now what I can do is get my ruler and I can join up all 3 points with a single straight line like this. Therefore, I can say that the line ABC is a straight line. Now, an alternative way of saying this that you need to be familiar with is saying that the points A, B, and C are collinear. Okay, so that's a key word. That means that they form a straight line. So both of those 2 sentences I've written down are equivalent to each other. Now let's take a set of 3 different points. So I'm going to call this point here D. Then we'll call this point here E. And then this point over here, we'll call it F. Now if I got my ruler this time and try to join up all 3 of these points with a single straight line, I will not be able to do it. I cannot get my ruler, so it's going through all 3 points at the same angle. Okay, what I could do is join up D and E like this. But then I'd have to draw a separate straight line to join up E and F. So I managed to join them up, but it's 2 separate straight lines. So you cannot say that DEF is a straight line. In fact, we would say the opposite. DEF is not a straight line. Or we can say that the points D, E, and F are not collinear. But what we have to do now is think about how we're going to show that 3 points are collinear. So let's go back and look at this straight line over here. And let's start thinking about vectors. What I want you to think about is the vector A to B and the vector A to C. And what is the relationship between those 2 vectors? Well, if you look at A to B and then look at A to C, both vectors will be going in the same direction. Now, if you have 2 vectors going in the same direction, we can say that they are parallel to each other. So A to B and A to C are parallel. Now let's take another pair of vectors on my line. So let's go with A to B, and this time we will go with B to C. Well, once again, if we look at A to B and B to C, they're both going in the same direction. Okay, so therefore, once again, they are parallel. And this is going to be key to how we're going to show that 3 points form a straight line. If we can show that 2 vectors on that line are parallel to each other, that is going to help complete our proof. However, there is going to be one other thing I have to mention in my proof. Okay, that is very important. So if I gave you 2 random points, and we'll call this point G, and we'll call this point H, and let's draw the vector G to H like this. Okay, and put my arrow on. Now I'm going to give you another pair of points. So let's go with the point I and then the point J. And let's say I was to join these 2 points up and draw on our vector. Those 2 vectors are parallel to each other. G to H and I to J are parallel. They're going in the same direction. However, clearly they do not form a single straight line. If I need to connect up all of those points, you cannot draw one single straight line. I've had to draw 2 separate ones. And the big difference between this scenario over here and the scenarios mentioned here is the fact that the vectors over here share a common point. Okay, if we look at my first sentence, these 2 vectors have the point A in common, whereas for the second pair of vectors, they have the point B in common. And that is going to be a crucial part of our explanation. To show that 3 points form a straight line, you need to find 2 vectors involving that straight line, but they need to share a common point. However, just be careful, we cannot pick a vector and its return vector. For example, you cannot do A to B and B to A, okay, because then we haven't used C. Okay, we must use C as part of our process. So we must have 2 vectors that share a common point, but all 3 points must be included in the vectors in some way. So the point C must be in at least one of the vectors, the point B must be in at least one of them, and the point A must be in at least one of them. So let's actually have a go at a question where we need to show 3 points form a straight line. So let's have a look at our question. We've got that ABCD is a parallelogram. So of course the opposite side lengths in a parallelogram are equal in length and parallel to each other. So therefore the vectors on both sides should be the same. Now we're told that A to B is 6A, which we can see written down here. So therefore D to C should also be 6A as well. And I am just going to underline my vectors just to make it very clear. And then C to B is 5B, which we're told here, and it's indicated on the diagram. So therefore D to A must also be 5B as well. So I've got those vectors now on my diagram. Let's continue reading the question. Now it says the line AB is extended to the point E. So therefore the line ABE is a straight line. And it's such that BE is equal to 2/3 of AB. Okay, because this is a straight line, and we're told that the length of BE is equal to 2/3 the length of AB, they're lengths because there's no arrow on top, we can also assume that the vectors have the same relationship. So the vector of the line AB is 6A, so the vector of the line B to E will be 2/3 of that. So B to E will be equal to 2/3 of 6A. So that is going to be equal to, we'd divide by 3 to get 2A times by 2 to get 4A. So therefore, this vector here would be 4A like that. And we'll probably have to use that later on in the question. Now let's move on to the next sentence in our question. So we're told that the point F is on the line BC. Now the point F is indicated here. If it wasn't, make sure you put it on yourself. Such that BF to FC is equal to 2 to 3. Okay, so we can see that the point F is on the line B to C, and this ratio here splits up the line B to C. So what I want to do is turn this ratio into fractions. I want to know what fraction of the line is between B to F and what fraction is between F to C. So we have 5 parts in total, and 2 of those parts are for B to F. Therefore, the fraction for B to F would be 2 out of those 5 parts. So it's going to be 2/5. So what I'm going to do is go to B to F. I'm just going to stick a 2/5 in here. And therefore, the F to C must be 3/5. Because those 2 fractions should add to 1 because they'd be the complete line. So I am also just going to write a 3/5 in here like that. Now let's consider what we're actually being asked to do. We need to show that DFE is a straight line. So in other words, the points D, F, and E are collinear. That's our goal. So in order to do this, I need to find 2 vectors involving that straight line that share a common point, and all the points D, F, and E must be present in at least one of the vectors I pick. So the vectors we could consider are D to F, D to E, F to E, or any of those return vectors. So you could do F to D, E to D, or E to F. Okay, you only need to find 2 of them, so don't find all 3, that is a waste of time. So let's just start with d to f. Now what you'll find is sometimes some of those vectors will be easier than other ones, but sometimes it will be hard to see that until you've actually worked it through. Okay, so we're trying to go from d to f here. We don't have any direct route from d to f. Okay, so we're going to have to go somewhere else first. So I'm going to go from d to c because I know that vector. So I'd say this is equal to d to c. And then once I'm at c, can I get directly to f? Well, I don't currently know the exact vector between c and f. However, I do have a fraction for that line. So that makes me feel I can find the vector c to f. So what I'm going to write is plus c to f down here. Now let's have a go at trying to figure out what these vectors are in terms of a and b. Well, d to c is the vector 6a. So I'm going to write a 6a in here. Now let's consider the vector c to f. So I don't know directly how to get to c to f. However, I know that c to f is 3/5 of the line from c to b. So therefore, c to f will be equal to 3/5 of c to b. So I'm going to write plus 3/5 of c to b like that. So now let's try and find c to b. So it's going to be 6a plus 3/5 of, and then c to b. Well, how am I going to do that? Well, I can go directly from c to b because I've got the 5b here, which tells me how to do that. So I'm going to write a 5b in here like that. Now let's simplify it. So we would have 6a, and then the 5 here will cancel with the 5 there. So we just end up with plus 3b like that. So that is my vector from d to f. So I am just going to circle that because we're going to need to use that in the final bit of my explanation. So that's d to f done. Now let's try and do d to e instead. So I'm going to write d to e here. And let's consider how we're going to get there. So we're starting at the point D, which I've got in green, and we need to end up with E. Now, if we're at D, what you can see is if we go upwards to A and then go across from there, we can get to E, and I know all of the vectors on those branches. Okay, so if we're starting at D, I'm first going to go to A, so it's going to be D to A. And then we're going to add on A to B. And then once I'm at B, I can then get myself to E, so we're going to add on B to E as well. Now let's replace all of those vectors and write them in terms of A and B. So D to A is 5B, and we're going with the arrow, so we'll keep it as positive. Then A to B is 6A. Once again, it's with the arrow, so we'll keep it as positive. And then finally, B to E is 4A. So I'm going to add on 4A like that. Now let's simplify. So I'd get 5B, and then we got two terms involving A, which give me a total of 10A. So we've now got my vector for D to E. So I'm going to circle that because we're going to make use of that as well. So that's most of the working done. What we now need to show is that these two vectors here are parallel to each other. So let's write D to E down here. So it's equal to 5B plus 10A. And now what we have to consider is are D to F and D to E scalar multiples of each other. Given that this is going to be a straight line, they should be if I have done things correctly. So the question is then, if we consider our A's, we've got 6A in our first vector here. We've got 10A down here. What do I multiply 6 by to get to 10? Now, if you're stuck with that, essentially what I'm asking is 6 times something is equal to 10. Now, in order to figure out this something, I would have to divide by 6. So that something would be equal to 10 over 6, which is equal to 5 over 3 if I simplify. Therefore, to get from 6A to 10A, I need to multiply by 5 over 3 like that. Now, let's consider my B's and just check whether this relationship of multiplying by 5 over 3 applies to my B's as well, which should be the case if they are parallel. So if I take the 3 in the 3B and multiply by the 5 over 3, will I get 5B? Which should be the case if they are parallel, but let's just check it. So I do 3 multiplied by 5 over 3. Well, the 3 here is going to cancel with the 3 there. So we're indeed going to end up with 5. Therefore, to get from 3B to 5B, we'd have to multiply by 5 over 3. Therefore, these vectors are parallel to each other. So let's write out my usual working for this. So what I found here is that if I take d to f and multiply by 5 over 3, I get d to e. Therefore, I can write that d to e is equal to 5 over 3 multiplied by my vector for d to f. So that is the 6a plus 3b. And then I can replace that 6a plus 3b with d to f, because that is what it's equal to. And then I can make my concluding statement that they are parallel because they are scalar multiples. So I can say, therefore, d to e and d to f are scalar multiples of each other. So they are parallel. I can then recognize that they share a common point of D, and then we can make our final conclusion that therefore DFE must be a straight line. So I'd say they also share a common point D. So DFE is a straight line. And that is a complete proof. We could also say DF and E are collinear, but given that the question mentioned straight line, I'm going to leave it like that. We're now going to build up to answering the toughest type of vectors question you can get at GCSE. So let's have a look at this one here. So it says find the values of lambda and mu. So just in case you're not familiar with these symbols, you don't have to be familiar with them. This is lambda and this is mu. Okay, these are Greek letters of the alphabet. Now, if we look at our equation here, we've got lambda and we've got mu over here. Okay, and lambda is multiplying A and mu is multiplying B. Now, on the right-hand side, we've got a collection of terms involving our vectors A and B. Now, what I want to do is write the right-hand side in a similar way to how the left-hand side is written. On the left-hand side, the A only appears once and the B only appears once. I want that to be the case on the right-hand side as well. So what I'm going to do is rewrite that right-hand side, and to do that, I'm going to simplify. So I'd still have lambda A on this side, plus mu times B, and their vectors, and that's equal to, and we've got 2a plus 3a, so that's going to be 5a. And then we've also got the 6b, take away 3b, so that is going to give me positive 3b left over. Now that we've written in this format, we can equate coefficients. The amount of A on the left-hand side should be equal to the amount of A on the right-hand side. So I've got lambda A on this side, and I've got 5A on this side. Therefore, lambda is equal to 5. So we found its value. Then on the left-hand side, we have mu lots of B. On the right-hand side, we have 3 lots of B. Therefore, mu must be equal to 3. And this is called equating coefficients. So let's look at a whole question. Okay, so we're given a diagram and we need to find the values of lambda and mu. So let's have a look at my diagram and see what we've been given and identify where is lambda and where is mu. Well, lambda and mu appear over here, okay, and that represents the vector going from B to A. So I can say that B to A is equal to this vector here, which is lambda A plus mu times B like that. Okay, so I now have a vector involving lambda and mu written out. However, there's no way of figuring out lambda and mu just by staring at the vector B to A. So in this scenario, what you're going to have to consider is there another way of getting from B to A? I know we've got the direct vector there between them, but could we get from B to A in a different way? So what I'm going to do is mark my point B, which is my start point, and then my end point is the point A up here. Okay, and we're going to think, how can we get from B to A using the other vectors on my diagram? Well, what I can do, I'm starting at B here. I can first go over to O, okay, because we don't want to go directly to A because that's the vector I've got written over here. So let's start by going from B to O, which is down here. So I'm going to write B to O. Then once I'm at O, can I get directly to A? Yes, I can, because I have the vector on the side length joining them. So what I'm then going to do is add on O to A, and we're at our destination. So now let's replace B to O and O to A with what they're equal to in terms of A and B. Okay, so let's start with the vector B to O. Well, that goes against this arrow here, so it's going to be the negative of that vector. So instead of positive 5A, we would have negative 5A. And then instead of negative 3B, we would have a positive 3B like that. Okay, so that's B to O. And then we need to add on O to A. Now, O to A is going to be this vector here. And we're not going to multiply by negative 1 because we're going with the arrow. So then it's going to be negative 4A and then plus 2B like that. Okay, and then let's simplify and collect like terms. So negative 5A, subtract 4A. Well, that's going to be negative 9A. And then if we do our B terms, it's going to be positive 3B plus 2B. So that's going to be positive 5B. Okay, so what I found here is a vector that is equal to B to A. So I'm just going to circle it here in red. But also at the top, I have a vector that is equal to B to A. So if both of these vectors are equal to B to A, they should be equal to each other. So what I can write is that the circled vector at the top, be lambda A plus mu B, must be equal to the circled vector at the bottom, the negative 9A, plus 5B. And you can see the vectors on both sides are in the same format. Okay, we have lambda lots of A here and negative 9 lots of A here. Therefore, lambda must clearly be equal to negative 9. And then on the left-hand side, we have mu lots of B. And then on the right-hand side, we have 5 lots of B. Therefore, mu must be equal to 5, like that. And that would be my final answer. Now we're ready to have a go at the toughest type of vectors question you can get at GCSE. So here's our question. OACB is a trapezium. Now in a trapezium, there's at least one pair of parallel sides. And we can see on our diagram, we have a 3B up here and a 5B as my vector down there. They're clearly scalar multiples. They're parallel to each other. And also in the question, we're told that O to A is 2A, which is also indicated on my diagram. So all those vectors are already on there. If they weren't, just make sure you put them on. So then we're told that OC and AB are diagonals of my trapezium and they intersect at the point P. This is quite an important sentence because what this sentence is essentially saying, if OC is a straight line and P is on it, then therefore OPC is a straight line. And then also the other diagonal, which goes through P as well, APB, must also be a straight line as well. Now let's start thinking about what this means in terms of vectors. Well, if OPC is a straight line, that means if you take any two vectors involving those points, they must be parallel to each other, because that's how we proved 3 points form a straight line. And the same can be said about the APB. So therefore, AP is parallel to PB, AB is parallel to AP, and so on. So we'll come back to that later because you'll see that's critical to answering the question. Now we're told to find and simplify an expression in terms of our vectors A and B for O to P. So let's start thinking about how we are going to get from O to P. Well, if I'm starting at O and I need to end up at P, let's think about where we can go. Because I don't know the direct vector from O to P. I don't have any sort of ratio or fraction involving the line OPC. So what I could do is go to A first. Now, do I know how to get from A to P? No, once again, I don't know that vector. I don't have any information about the line going through A, P, and B. Okay, so where else could we head? Well, we could head to C, then ask ourselves the same question. Can we get from C to P? The answer would be no. And then we're sort of at a bit of a dead end. So let's go back to O, and let's go in a different direction. Let's go to B first. Well, if I'm at B, do I know how to get to P? No, once again, I don't have any information. So it's starting to feel like I don't have enough information in the question to be able to answer it. And it's at that point you know that you have identified the hardest type of vectors question you could get at GCSE. And we're going to have to approach this question in a slightly different way. What we're going to have to think about is which vector do we know is parallel to O to P, the vector we're trying to find. Well, O to P is on the straight line O to P to C. Therefore, any vectors involving that straight line must be parallel. So O to P is parallel to P to C, and O to P is parallel to O to C. Now I'm going to use O to C because C is one of my vertices and we have a lot of information linking up the vertices in this shape. So O to P is parallel to O to C. Therefore, O to P and O to C are scalar multiples of each other. So I can say that O to P is equal to some scalar multiple I'm going to call K multiplied by O to C like that. Okay, K is picked randomly. You can pick any letter, just don't pick one that's already present in the question. Now, this statement must be true because they are parallel. And what I'm now going to do is try and find O to C instead and multiply by K. So how would I get myself from O to C? Well, that's fairly straightforward. I could do 2A up to A. And then once I'm at A, I could then do 3B to get across to C. So I'm going to add 3B on like that. Now I could expand the bracket. So 2A times K is 2KA. And then K times 3B would be 3KB. So I found a vector representation of O to P in terms of A and B, but we've also got this scalar K. Now it's not going to be possible to find K just by staring at that vector representation there. What you're going to have to do in this type of question is think of an alternative way of getting from O to P. Okay, so I'm going back to O and starting from there. And just think, where could I go first? So we've got a couple of options. We could either go to A or we could go to B. It's actually up to you. We can get the correct answer picking either method. So I'm just going to take this information off here because we've already used that. And we will use it again, but I just want to make a bit of space. So I'm going to write OP again. And I'm just going to circle what I had before because we're going to come back to that later. And then we said you need to start by going from O to either A or B. So let's go from O to A. Okay, so then I will find myself at A up here. Then we need to get from A to P. So I need to add on A to P. However, the issue as discussed earlier is I don't know what A to P is. As we've already done in this question, we now need to think about parallel vectors. We need to ask ourselves, what vector is parallel to A to P? Well, A to P to B is a straight line, so any vector on that straight line are parallel. So we can say that A to P is parallel to P to B. We can also say A to P is parallel to A to B. Now I'm going to use A to B because B is one of my vertices and it's very easy to move between the vertices. So I'm saying that A to P, what I'm trying to find, is parallel to A to B. Therefore, what I can say is that they are scalar multiples of each other. So A to P is equal to some scalar multiple that I am going to call T multiplied by A to B, the parallel vector. So now I've got that. I now have to think about how I'm going to find A to B in terms of A and B are vectors indicated on the diagram. So I'm going to write plus T, open brackets. Now if I'm starting at A and I need to get down to B, well, I could go from A to O first. And then once I'm at O, I can get along to B. So I'm going to add on O to B like that. Now let's replace all of these vectors for what they're equal to in terms of A and B. So let's start with O to A. Well, O to A is just equal to 2A here. So I'm going to put in 2A. And then we got plus T, lots of, open my bracket. Well, if I want to get from A down to O, I'm going to have to go against this vector, so it's going to be negative 2A in here. And then once I'm at O, I just need to do positive 5B, and that is going to get me to B, my destination. Now let's expand the brackets. I have T multiplied by negative 2A, so that's going to be negative 2TA. And then T multiplied by 5B, so that's going to be plus 5TB like that. Okay, and this is a vector representation of O to P. So I'm just going to circle that there because I can't figure out T just by staring at that vector there. What I have to consider is the two vectors I have circled in green because I have O to P is equal to this representation here, and then O to P is equal to this representation here. Therefore, those two circled parts in red have to be equal to each other because they're both O to P. So I'm going to write out the top one, which is 2ka plus 3kb, and that should be equal to the one at the bottom, which is v2a subtract 2ta plus 5tb, like that. Now, if we look at my left-hand side, we've got two terms written. A appears once, B appears once. So I like that, but the right-hand side doesn't match that. Okay, B does appear once, so that's fine. However, the A is the problem, and that appears twice. So on the right-hand side, I'm going to factorize out A so that it only appears once. So I would get A outside the bracket, and then that would be multiplied first in the bracket by 2, and then by negative 2t, like that. And then I've got the plus 5tb outside my bracket there, like that. Now both sides are in the same format, we can equate coefficients. If we have 2ka on this side, okay, that means we have 2k lots of A. Well, the amount of A I have on the other side in terms of how many lots is 2 subtract 2t. So therefore 2k must be equal to 2 subtract 2t. We're equating coefficients. Now let's consider my b's. Well, I got 3k lots of b on the left-hand side. We got 5t lots of b on the right-hand side. So 3k is going to be equal to 5t, like that. So we now have a pair of simultaneous equations which we can solve to find either t or k. And once I get either t or k, I can then substitute them back into my green, red circled vectors on the right, okay, and get my final answer for O to P. So I should only have to find one of k or t. Once I've got that, I can make use of it to find O to P. So let's go to my simultaneous equations. Now, could I simplify either of them? Well, this left one here, I could divide by 2 throughout. So I'd get 1k is equal to 1 subtract t. And then we need to make either t or k the subject of this here. Well, k is already the subject. So we can now go and substitute this into my other equation I haven't used yet. So I'm going to replace the k with 1 subtract t, because that's what it's equal to. So I'd get 3 lots of, and then it would be 1 subtract t, and then we can write out the rest of the equation, which is equal to 5t. Then to find t, I'm going to expand my brackets because I've got a single variable equation. I'd get 3, and then subtract 3t is equal to 5t. Then get your t to one side. So we're going to add 3t, so we get 3 is equal to 8t. And then divide by 8 to find what t is going to be. The t is going to be equal to 3 over 8. So I found my value for t. So what I now can do is go and substitute it in to this expression here to find O to P, which is going to be my final answer. So O to P is going to be equal to, and then we've got 2a here. And then we've got next, we've got subtract 2t times a. So I'm going to write subtract 2. And I'm going to sub in my value for t, which was 3/8. So I'm going to put 3/8. And then I'm going to write my a in. And then my final term is the 5tb. So I'm going to write 5t, but in place of the t, I'm going to put the 3 over 8. And then finally, I'm going to write in my b here. Now, all we need to do is simplify. So we'd have 2a. And then this negative 2 would multiply up to the numerator because it's a whole number. So we would get negative, and it's going to be 6 over 8, lots of a. And then similar would happen for my next fraction. It would be 5 times 3. So it's going to be positive, and then 15 over 8, lots of b. Now we can simplify my fraction in front of the a. It's going to become negative 3 over 4 if I divide by 2 on the numerator and denominator. And then we got the 15 over 8b. Then the last thing I need to do is simplify my 2a, subtract 3/4 of a. So if we write the 2 with a common denominator of 4, it would be 4 here, and then an 8 in the numerator, and I have an a here. And then subtract 3/4 of a plus 15 over 8b, like that. So then 8 over 4, subtract 3 over 4, well, that's going to give me 5 over 4, lots of a. And then we got the plus 15 over 8, lots of b. And that would be my final answer for O to P. So we have managed to answer the toughest type of question you could get for vectors at GCSE.